Good morning again. Today we're going to continue and finish chapter 8. Last time we started with human physical interfaces, input devices. We talked about the keypad. We wrote. Yeah, there are. If you remember, we had some. We spent a lot of time here. Then I figured out that I was trying to do something to read the keypad in a way. This is what they do in the lab by writing a row by row 4 times and always keep reading the column. That's one way. The other way is the one presented here, and we wrote the code for it on the board here. Okay, then we talked about the 7-segment display, common anode, common cathode. How can we use the anode or cathode to enable a 7-segment display? And I explained how these 7-segment displays are connected in our board through port D and how they're enabled through port A. And we wrote the code to display a counter on the 7-segment display from 1 to 10. Then another example for another counter to display a counter from 0 to 99 on 2 7-segment displays using time multiplexing. And I had a question for you here. The way, we use timer zero for 2 purposes. We used it, and if you want to see it here on the code, we used it for 2 purposes. The first purpose was to increment the counter every second. So we used the overflow. We made it overflow every 32 milliseconds. Then we counted a tick every 33 ticks. That's 1 second almost. We incremented I, and then we went into ones and tens, and quotient and remainder, and displayed it on 2 7-segment displays. And I think it's still open. Yes, شايفين. So this is the first use of timer 0, the overflow. The second use in time multiplexing technique, you need to enable one of the 7 segments, display on it a number, then you enable the 7 segment and display another number and do the switching really fast. We did it in 2 milliseconds. Okay, so I use timer 0 by looking. If you want to remember what I did, go back to the recording last time. But every bit in timer 0, bit 0 flips between 0 and 1 every 128 microseconds. Bit number 1 flips every 256 microseconds, any slower, half time. Okay, bit number 3, half of that time. Bit number 4, half of that time. So if you want really, if you remember timers, counters, every bit in a timer. Can we call it a frequency divider? Yes, it is a frequency divider. So if you have timer 0, that increments every amount of time. It's 8 bits, but I'm doing it for 4 bits. 3, 4, right? 5, 6, 7, and so on. So if this bit flips from 0 to 1 every t, then this one flips every 2t. So this one flips every 4t, 2 times the one before. This one 8t, right? And so on. So we can say if bit number 3, if bit 0, 1, 2, 3, if timer 0 and mask bit 3 equals 1, then do something else, do something. The amount of time you're going to spend here is 8t, right? The amount of time you're going to spend here is 8t, and this is what we did last time. Okay, but is this the only way? Is it you can do something different. You can say turn on, this if You say port A, enable the second digit, the second 7 segment, display the quotient on it, do delay for 2 milliseconds. And we wrote a function to do a delay, right? Do delay for 2 milliseconds, then enable the other one, display the number on it, and do delay for 2 milliseconds, and so on. Keep doing it forever. You don't have to do it using timer 0. This was just an idea I thought about. Right. So we did this example. Today we're going into a new topic, but related to interfaces. We're going to look at some very famous sensors, and you were given an assignment, right? I mean, research assignment to look at 10 different sensors and look at the main characteristics of each sensor and how they operate, or the principle of operation and how they work. What are they used for some sample applications? And I think that gave you some insight about sensors. I'm going to cover some important sensors that a lot of you guys in your projects usually use them. I'm going to talk about a microswitch, light-dependent resistor, which is a light sensor, optical object sensing, ultrasonic, optical using several. I'm going to talk about 2, I think, kinds of sensors using IR, ultrasonic, Hall effect, and temperature sensors. The microswitch is the easiest, and if you see this part, it's a switch, and it's like a push button. And if you put it on the front of a robot, see this bar, if the robot hits something, this will be pushed inside, then a button here inside, and this switch will be pushed. So it's actually a push button. So to interface it to your microcontroller, you need, see this pull-up resistor? You need a pull-up resistor to the voltage source and ground. And if you hit, then this button is pushed. As simple as that. So you can detect if you hit something or not. A micro switch. Another kind of sensors is light dependent sensors, LDRs, or they call them light sensors. Light sensors. They detect the brightness or the light in a room, the amount. Some of them are digital, some of them are analog. The basic concept of this light sensor is that it's a resistor. This resistor value changes depending on the light in its surrounding. So if this resistance changes, you can put it in a voltage divider setup, and this voltage will change depending on the value of this resistor. If you increase it or decrease it, the voltage will change, right? So you can say, you can take this value, this voltage, to port A0, which is analog 0, right? You configure this as an analog voltage and convert it to a 10-bit, and this is 10-bit number, okay? And if you want to detect on/off, use it in a manner of to turn on the lights or off the lights when it's dark or not. You can calibrate that, right? You can set the amount of lighting in the room where it is acceptable, and then start dimming it down, or put something around it until I say, okay, now this is dark, I want to turn on the lights, and you keep reading this value. مثلا, when it's fully dark, the value is the resistor is high, so the voltage is larger than 4.95, okay? Then the reading is going to be something, if we are using a 10-bit A to D, the reading is going to be something close to 1023, and أقل, يعني هذه can go 10,000, 1,000 something. So this is fully dark. If it's less than, let's say 1,000, the number was that you read here. Lower than, if the reading is lower than that, then we're more brighter, the voltage went down, right? So at 2.3, if we're reading voltage range from 0 to 5, then this 2.3 will be something around 512, right? Medium dark, if you want. Fully bright, the voltage is going to be very small. The reading will be less than 100. So you can say if then else. If you want it to be fully proportional, you can take this number you read here, convert it. If you have a PWM light, a microcontroller, to turn on the light here, instead of doing a 1 or 0, you can do a PWM, right? And the more time you have the high, the brighter the LED is going to be. So you can take this reading, multiply it by a factor, convert it to time, right? And have the light be there and stay proportional to the resistor reading, the LDR, sorry, the sensor reading. This is about light depending sensors. Some optical sensors that rely on optics, a kind of light or waveform in the light region. There are many sensors that use this feature, especially the infrared spectrum. There's one sensor called a reflective sensor. It looks like this. This is actually two parts. This is a part, and this is a part, but it's packaged in a way. One of them is a transmitter. The other one is a receiver. This is the transmitter. It's an LED IR transmitter. You just power it, power, ground. It transmits an infrared wave. When it hits a surface, it reflects, okay? It reflects. Then this receiver part will do the connectivity here. So this is like the gate or the base. Depending on the amount of reflected IR, the connectivity here will change. So if you put here a voltage source and this to ground, right? So the voltage you read from here will change depending on the amount of infrared that reflected from the surface. So if this surface was a white surface, the reflected IR is going to be different than if it was a black surface. If it was smooth, it's going to be different than a rough surface, and so on. So the way you connect these two bits, this transmit part, one of the pins you take it to ground, right? This is it. You take it to ground. The other part you take it through a resistor to the voltage source. And this part, you take the emitter to ground, and you connect this through a resistor to the voltage source. And below the resistor here is your V out, and you take it to your microcontroller, and you can do it as, depending on the voltage you get here, you can put it before on a scope, and do some calibration. Bring some surface, put it in front of it, put a white surface, and see what is the voltage going to be. Then get a black surface, see what the voltage is going to be. If the voltage levels are clearly low or high, you can connect it to a digital pin, right, and see if the surface is white or black. But if the voltages are very close to each other, you can take it to an analog pin and read the amount of voltage, be able to figure out the voltage is 3.1, then when it was white, and the voltage was 3.6 when it was dark. And then inside your code, the 3.1 will be represented in number in 10 bits if this number was greater than this, then white, else black. So why is this useful? This could be very useful in many applications. And this is one application. This is a reflective sensor. This is a wheel that is turning. And a way to figure out the speed of the wheel, the RPM, if you want to measure the RPM, rotations per minute, how fast does this wheel turn, or this motor turn, if you want to do a motor control, speed control for any purpose, for controlling the speed of a robot, controlling the speed of, I don't know, of anything that turns. One way is to do a reflective sensor, just get some pieces of paper, black and white, in stripes, and you will get a different reading when you're at the white place than black place, white place, black place. Right? So if this was the wheel, you can split it into two parts, black, white, right? And put your sensor here, fixed, and this will turn. So half of the time it will read black, half of the time it will read right. So you say in your code, if you read, if you were black and move to white, so you can put it in an interrupt. If reading of the sensor was above a threshold, reading was above the threshold, then black, else white. So you can put this in an interrupt and do it every millisecond or whatever. And if then a transition happens, you can increment a counter. If a transition happened, you can increment a counter, then you moved from black to white, right? And every time you move from black to white, then rotations plus, right? Then every amount of time, a minute or half a minute, divide by half a minute, you get RPM. But the accuracy is not going to be very accurate. If you split it in 4 parts, then every 4 transitions means a 1 RPM, صح؟ يعني you get to know RPM, not a full RPM, حتى ربع RPM. If you want to split it into 8 parts, see, like this here, black, white, black. So every transition means 1/8 of a part or 1/6 of a part of a rotation. Just an idea how to use this sensor. This is another kind of type of IR sensor, but we use it. This type of sensor, we call it. What do we call it? We call it rangefinder. It's an IR sensor زي اللي قبله. It uses more power. It consumes more power than this one. Needs higher voltage. It is used to measure distances or a range, usually from 10 centimeters. Now, today we have something maybe 2 centimeters, up to 80 centimeters, and some even started going beyond. So the way this works, that there's an IR transmitter that transmits a waveform, an IR waveform. If an object is in front of it, it will reflect back. Oops. This will hit a surface, reflect back. Okay, it will be detected by this IR receiver. Now we know the speed of light, right? You know the speed of light, and you have the control to trigger it and say transmit an IR signal. Then you know when you read the IR signal. If you know the speed, you know the time when this went out and came back, right? You know the speed of light. You know the traveled. You know the time to travel, right? Then you can compute both of these values, you can compute the distance that this signal travels. The distance divided by 2, then the distance traveled going and coming back, right? So divide the distance by 2, then you will know how far this obstacle is far from your robot. If this is put on in front of a robot. This is usually, in this kind of setup, if you see the wires, the red is the voltage source, the black is the ground, and the yellow, sometimes it's orange, sometimes it's orange, is V out. Usually these sensors are analog sensors, which means you connect it to an analog to digital converter pin, right? And your MCU connected to AN0, which is port A0. And you will be able to read a number from 0. You read a number, the reading will be a number from 0 to 1023. Well, you can calibrate this. Before putting this to the microcontroller, put it on a oscilloscope in your lab. Put some obstacle really close to it, and read the voltage, and start bringing get a piece of paper, put it in front of this, and start taking it away until 1 meter, and see how the voltage changes between 1 or 2 centimeters up to 80 centimeters. Okay, you will understand how this measures, right? Then you can read it into your A to D, get a number. The number will be, if the voltage was small when you were very close and got larger when you're, or vice versa, when you got away, then the number will reflect this, because the number is the voltage, right? And the 1023 is 5 volts, the 0 is 0 volts, and everything in between is proportional. Now, who triggered the light to go, and when it came back, who did this math and gave you a proportional voltage? Usually these are called smart sensors. This is a smart sensor. That's why it's a little expensive. I think I'll tell you in a second. So this is usually a smart sensor. It has a controller inside it that tells it, okay, trigger, read back, convert it to voltage, and display the voltage on a pin, and then we read this pin on our microcontroller. When we were back on campus, I was in the lab, and some of your colleagues were doing experiments using an IR sensor. Then I discovered that they were using a digital IR sensor. The IR sensor sent back a signal, high or low, if there was something in front of it, period. And how far is this thing? It doesn't matter. If there was a threshold, and on the board of that had the IR transmitter and receiver, they had a potentiometer to change this threshold. Okay, that kind of sensors, IRs, are digital, so you can take it to a digital port. If you read a 1, then there's something within a range. If you read a 0, then it's clear to see that there's something in front of you or not. But this one gives you a proportional voltage, which means how far it is then from you. It is 10 centimeters, 20 centimeters. It can be very useful to control the altitude of small helicopter from ground in landing, and we're getting closer to ground. Or a robot to get precise and touch things smoother. Ultrasonic rangefinder. This is also a rangefinder sensor. Ultrasonic. It can come in different ways, in different types. This is one common type here. So I asked for the IRs I didn't see these. I know in the past we had them. The digital ones are cheap somehow. These are more expensive. I think they're like $30 to $35. The sonar sensors, instead of transmitting and reflecting back an infrared waveform. This transmits an ultrasonic waveform. Okay, so a transmitter and a receiver travels at the speed of sound, hits something, reflects back. You know the speed of sound. You know when this thing was triggered out, when it was received back, then you can compute the time of travel and divide it by 2, so you can compute the distance between the sensor and the obstacle in front of it. The ones that are the cheaper ones have several pins, usually voltage source, مثلا, ground, then trigger pin. So you write a 1 here for some certain amount of time to trigger the signal out, and a receiver pin that you wait for, it stays low. When this is received back, it goes high. So you need to measure the time from when you triggered until you detected something here. You measure this time. So the use of timers, interrupts here is very useful. This time is proportional to the distance between this sensor and the obstacle in front of it. So if you want, you can do it reading data sheets, or you can just easily connect this voltage to a scope and measure the time it took you since you gave a signal here to this to come high back, measure the time and see how this time is dependent on the distance in front of the robot. Usually, sonar sensors are used to measure 20 centimeters, 30 centimeters. Now I started hearing about something more and even less, up to 7 meters. Yani IR, usually we don't use them more than 100 centimeters or 1 meter, but sonar, we use them to measure distance up to 7 meters. But for very low, below 20, they become inaccurate. And the reason is the speed of sound, ultrasonic sound waves is much less than IR. So, and this is also, it could be a smart sensor with a board on it. So it couldn't have maybe it will not be able to do the proper computation of any, if this was very close, triggering something and reflecting, coming back, it will not have the time to compute. So usually they're used for distances more than 20 centimeters. Some more expensive ones look like this. I used this one many times. And these are ranges of prices a few years ago. I'm not sure, I didn't check them recently, but I expect they're still in this range. This one can give you the reading in 3 different formats, either analog, V out, and you just take it to analog to digital converter, or PWM, it gives you a signal with a pulse width that is relevant, proportional to the distance. So you can use a capture, compare PWM module to measure the time between, or use timer 0 even. So we talked about this in chapter 6, how to measure time between a rising and a falling edge, right? And this distance depends on the distance of the obstacle in front of it. The third way could be serial. You just get a number, 1 meter, 2 meters, 1.5 meters, whatever. So this is if in this case, this would be a smart sensor with a microcontroller on board that does this math for you and sends you the reading straightforward, that you can read through your serial communication. Another type of sensors, it is really easy if you want to see it in a practical. I cannot do a demo on each one of these, but if you want to use any sensor, get its data sheet. You can Google it, see how it works, but most of them have the same concept, especially the analog. The Hall effect sensor. Hall effect sensor detects if there is a magnetic field around it. So if this is the Hall effect sensor, if there is a magnetic field close to it, the voltage you get, so when it has 3 pins, one of these pins is the voltage source, the other one is ground, right? The third, this one could be a digital out or analog. Some of them have analog output, or it could be digital output, which means you get a 1 or a 0. If there is something close to it, the analog ones, you use them to detect how far a magnet is from this sensor, and it could be used in many applications. And one of the applications I used it in is to figure, مثلا, a robot arm, how far, if you put a magnet here, and this is metal, and you want to touch something really really smooth and precise, you don't want to hit it toughly, you can put a Hall effect sensor and read the voltage you get from this, and you get a different voltage. You see the voltage changing as you get closer or getting further from this object. If digital, it can be used to detect if there is a magnet field around or not. It is very useful. Some of the applications people use it for is to do RPM as well. And if you have a bike, مثلا, a bike or any wheel, you can put a magnet on it, and here you put a Hall effect sensor. Hall effect sensor here is a magnet. If this is turning, and you get a digital signal, so you get a pulse, a 1 every time this magnet is close, then a pulse, right? So the number of pulses within a time period, these are the rotations per minute. If you put 2 magnets, a magnet here and a magnet here, then you will count double the time, but you'll have more resolution, half of the rotation. So many useful applications. Temperature sensor, also analog. So this is a microchip sensor, very common. I saw it, we have it in our labs. It comes in different packaging methods, and usually it has 3 pins, voltage source, ground, and you get this V out. This V out, you take it to the A to D on your microcontroller. Take it to the scope if you want. To the scope, you'll see the voltage changing up and down depending on the temperature surrounding this package. Okay. Many useful applications to measure hard disk drive, temperature, entertainment systems, home appliances, office equipment, battery packs, to measure temperature of anything if you want. Now, we get a voltage, right? We get a voltage here, but how does this voltage translate into temperature? Same as how does this voltage translate into distance? In the data sheet of sensor, this formula, if you go Google microchip MCP 9700, you will get a data sheet. And I took a snapshot of this data sheet. And this data sheet is for 2 kinds of sensors. This was 9700 and the 9700A. It gives you a formula how to translate the voltage into ambient temperature, the temperature surrounding the microcontroller, surrounding in the room or in the around it. So when you put the sensor, you connect it this way, you give it power and ground, and take this V to the analog to digital converter. So you read it, and you read the reading was 512. If the sensor is a 10-bit, if the A to D was a 10-bit A to D, then the reading you should get for 0 volt to 5 volt is a number from 0 to 1023. And this is, again, I explained it in the A to D chapter, right? So if you read a reading in the A to D and it was 512, 512 is converted, if you do proportional, is 2.5 volts, right? So you know the volts, you know the voltage when you read a sensor. You get a number 512, then this is 2.5 volt. طيب, how do I know if I read 5 volt? What's the temperature outside? Well, the temperature outside is, so voltage at 0 Celsius is a given here. If we have the 9700 microcontroller, the 9700 microcontroller gives me a voltage at 0 Celsius 400 millivolts. Hey, okay, 400 millivolts. So this is 400 milli. Temperature coefficient, which is temperature coefficient here of, it has 10 millivolt change per Celsius. So this is 10 millivolt per Celsius. And the V out you get from the microcontroller, you know it, you just read it here, right? And it was 512, you did the math, converted to 2.5. And we did this exact example. We converted a voltage to, you converted a voltage on a 10-bit A to D into a number between 0 to 5. So you get 2.5 here. So this is 2.5, مثلا. So what is TA? TA will be temperature outside when the reading is 2.5 equals to V out, right? V out minus V at 0 Celsius divided by temperature coefficient, right? And this equals to V out, the voltage you read is 2500 millivolts, 2 volt, right? Minus 400 millivolts over 10 millivolts per Celsius, right? But in the units, take the units out, you get a Celsius. And this is 2100 divided by 10, right? 2100 divided by 10. Then the temperature outside is 210 Celsius, which is too large. So you don't expect to get a voltage 2.5. So the voltage could be something below, for sure below 2 volts. And you get in the data sheet, you will see the numbers that are, in this case, this sensor measures values between minus 40 Celsius to 150 Celsius. Okay.
طيب ممكن سؤال بس؟
تفضل قيس.
هلا طب مش أحسن كنت مثلا لو إني عارف مثلا مش صعب يطلع عن 2.5، أخلي 2.5 بس لحد 2.5 هي السكيل على 10 بت، ولا خلاص يكون سكيل على 10 بت تبعت الأنالوج تو ديجيتال؟
والله again مدريش الصوت صار يقطع شوي مرة ثانية سمحت.
هلا سينس مثلا إحنا شفنا إنه 2.5 تطلع 210 سلسيوس which is impossible. فليش ما أعمل أنا سكيلينج ل 2.5 على 10 بت مش 5 فولت على 10 بت؟
لا this was an example قيس. This was an example يعني it's impossible صح يعني you're not gonna يعني you know what, let me do it. MCP 9700. Well, why should I do it? It measures a temperature between minus 140 Celsius to 150 Celsius. هسا minus 40 Celsius to 150 Celsius, we can compute what is the voltage, صح? That the V out you get in both cases. So if we get this one, طيب يعني since already the time ended, it's okay to, and it's recorded. The voltage out يعني equals temperature coefficient, right? Times ambient temperature plus voltage voltage at 0 Celsius. صح? This was it?
Yes.
Let me make sure. Yeah. And voltage coefficient was 10 millivolts and minus 40 to 150. Huh? Minus 40 Celsius to 150 Celsius. 150 Celsius. Voltage coefficient is 400 millivolts. And temperature coefficient is 10 millivolts per Celsius, right? So usually this is something you know. You read it, and you read it actually in your microcontroller. صح? This is so you compute the temperature. This is the usual case. طيب, can we guess what is the voltage range we get? يعني if the temperature outside was minus 40, what would be the voltage? If the temperature outside was 150, what would be the voltage? Just apply it, صح? So 10 millivolts times minus 40 Celsius, صح؟ زائد what is this? 10 400 millivolts. And if actually I want to get the actual data sheet, I think I have it here. No, let me search for it. It gives you, this sensor is called MCP 9700. Okay, MCP 9700. If I go Google MCP 9700, here, thermal microchip temperature sensor. Linear gives me 10 volt for each Celsius. Here, accuracy plus minus 4 Celsius from 0 to 70 Celsius. Minus 40 to 50, the accuracy changes. Very low operating voltage, current, sorry, to 12 microamps. Max operates from 2.3. Hey, this is the voltage. From 2.3 to 5.5 operating voltage. This is the voltage you can give it as any voltage source. No external component required. طيب. View data sheet. Here is it. And this is actually this snapshot I got for you, صح ولا لا؟ 9700. Storage temperature, ambient temperature minus 4 to 70, output current, injection temperature, temperature at 25 Celsius, accuracy is typical plus minus 1 Celsius. Yani operating voltages, minimum is 2.3, maximum 5.5. The currents you get.
أنا أتوقع هي تحت بالسنسر
output voltage 500 millivolts per Celsius, right? At 0 Celsius, sorry. هذا for the 9700. The other one is 400. Temperature coefficient 10. Output non-linearity. See, 0 to 70 is different than below 0 and above 70. Yani you need to dig deeper, to check out all the details when you want to use it. This is really rough. Specified temperature range. This is what we looked at. Typical performance curve. This is a typical performance curve. So accuracy this is from ambient temperature minus 50 to 150. At minus 50, this is the accuracy. Do we have temperature versus voltage? Output voltage at 0 Celsius, see? This is the output voltage at 0 Celsius, output voltage. Occurrences versus temperature coefficient, line regulation, change in Celsius per voltage, change in voltage, how it affects, يعني شوف. Okay, voltage output versus power. output voltage for the ambient temperature. This is the one you want, right?
إيه على اليمين.
This is it. So look at it. So at minus 40, the voltage you get is something point. If this is 0.5, if this is nearly 0.1 volts تقريبا minus 40 up to maximum at 125 when he shows us is like 1.5 1.7 or 1.8 volts, right? This is the other type. Yeah, so at the end of the day, you're going to read voltage depending on the temperature. You apply that formula. You apply that formula I showed. Yeah, this one. This is it, right? Yeah. You apply this formula. You get you know this voltage. You read it. It's an output of the sensor. This is what you sense. You know these numbers, and you compute the time, the ambient temperature. Okay, let's go back. طيب, what is this? And I'm picking some topics from this chapter. Only 6 people left, huh? طيب. I'll move faster. Ensuring legal logic levels. Yani some of the things you need ways to ensure legal logic levels when you input any kind of voltage coming from a sensor مثلا. Sometimes you can get a spike, sometimes you can get some noise, إلى آخره. One way is to have protection diodes to protect against instabilities in the voltage sources. One way is to have a low pass filter like this, right? So if you get something with high frequency, you filter it out. Or you can use a Schmitt trigger, right? Hysteresis, and we explained this before. You can use optocouple, yani IR transmitter, IR receiver, so you don't have any physical interface between two systems, right? You have completely separation if you are worried of this voltage levels, spiking, noise, even the ranges, right? So you can completely isolate a system here from a system here. Interfacing switches. This is an issue when you interface a push button or a switch مثلا. If you interface a push like this. Oops, what happened? If you interface a push button like this. When you push the button, this contact, this is a metal contacting a metal, right? So the bouncing may happen, bouncing. So the voltage source was high before you push the button. When you push the button, it's slow, it becomes low. But in between, the bouncing could cause going up and down for a while, right? So if you're reading this sensor through pulling, every time in your loop you say, read port B, it was high. Read port B after a certain amount of time, it was high. Read port B, low. Now I know it's low. So even though this is a disadvantage of pulling, and we did examples right before when we were learning interrupts. I push the button, nothing happens until after some delay, because until we got to execute this instruction that reads. So see, the actual button push down happened at this point, while you were able to figure it out or notice it at this point, because the time between the reading is this was high. It could occur like you push the button, you read right away. So the time you figure it out could be immediate, but due to the bouncing, you may be this single point when you read it, it was low. So you have an error here when the debouncing ended, to be able for sure to make sure that was low. So you can have an error. A way to solve this problem is to detect the falling edge, and you don't care what happened afterwards, right? So you can use an interrupt to read the switch. This is one way, debouncing. And this is in software, some do it in hardware. Moving to actuators. Some of the famous actuators that you guys usually use in the lab in your projects are motors. There are, and I'm going to talk about these famous four types of motors: brushed DC motors, brushless DC motors, stepper motors, and servo motors. A brushed DC motor is something you guys are all familiar with, صح? Did I put any links here? It is really
معروف
handy. معروف. Oh, thank you. brush
نستخدمه
brush. Yeah, just Google brush and you can see animated videos, very useful. It's just like this one we used in our example last time, right? You give it a voltage level, and what happens inside? You have a winding, صح, around the core, and when it turns 180, the brushes will flip the voltage level, so it will continue التنافر هذا and continue rotating. Brushless DC motors, they don't have brushes inside to flip the polarity or the magnets. It's done by a controller. We call it a motor controller. So with every brushless DC motor, you have a motor controller that does this control to flip. What's inside the brush DC motor is something like this. You have winding, you have brushes here to flip the I don't know why this okay, to change the polarity. In a brushless DC motor, you could have multiple windings, and the brushless DC motor controller can change. Oh man, make this active, so the to cause the core to rotate for some distance, then makes this active, then and so on. So you change the magnetic field applied to this core by a controller, a computer, a small brushless DC motor controller. Benefit of this, it's brushless, so it can go very high speeds, lives longer, and the main feature is the speed. And we use them a lot. And if you see the UAVs, drones, these things, the vertical takeoff and landing UAVs, we use usually brushless DC motors. They give us really good high speeds. Stepper motors. Stepper motors. Actually, I got the screenshot from Wikipedia. They had just go put stepper motor and Google get a good animation. A stepper motor, you have for the motor, see, you have several wires going out of it. You just take these wires, and one of them is ground, of course. You take them, the ground, take it to ground, and then take these two. This is for port B0, port B1, port B2, port B3, مثلا. So you write a 1000. This will move one step. شايفين this gear? It will move one step, very small step. Then you write a 0100. It moves another step. 0010, another step. 0001, another step. Then you go back again. You put the one here and everybody else zeros. Then you put the one here and everybody else zeros. So every time you increment, you cannot jump. You cannot write a one here, then the one comes here in the next cycle. No, it has to be step. That's why you call it stepper motor. Okay. Usually it's a very strong motor, and you can hardly move it by your hand. Usually one of its characteristics also says for a full cycle it takes مثلا 200 steps. So very precise to make you move something you want to move. For a DC motor, there is no position control on it, right? For this DC motor or this one, there is no feedback, so I can know مثلا if I connect an arm to this, right? An arm. There is no way of feedback method to know how far this arm moved or how fast this motor turned. But for this one, since you control step, I know 100 times. If I put this in a loop, yani 10, yani 1000, if I put it in a loop for, if I know that I need 200 steps for this to rotate a full cycle, and and I have 4 lines, so I need to do for 50 times, 50 times, صح? 50 times ضرب 4 times 4 equals 200, right? So put on line 1, 1 and everything else zeros, and then line 2, put on it 1 and everything else zeros, then line 3, then line 4, activate it, and repeat this for 50 times. So we've moved 4 steps here, times 50, this is 200 steps. So you have a full rotation. So you know exactly, if you have 200 steps for a 360 rotation, you can know how many degrees you moved. So you have a sense of feedback here. So if you have an old printer, for example, an old inkjet printer that pulls you put a paper in it, the paper feeder takes the paper, right? It knows how far to pull the paper. Then the inkjet head starts moving back and forth and moves for a certain amount of, for a distance that is well known. It usually, if you have an old one, just get it apart. The motors that move the feeder and move the heads are usually stepper motors. Okay. If you don't want to do this, wire them to wires and do this math and loops. Usually, you can buy a stepper motor controller with it, a chip, where you just require, مثلا, you just require the angle you want to move, and it does everything for you, or the speed. Another type of motors, and I think I got some on here, is servo motors. Servo motors. Servo motors are also types. Some of them, and sometimes I think you guys, the interested guys, if you want, we can do some demos later. I want to shorten the recording a bit, because last time it took like 3 days to have it ready. Anyways, servo motors look like this. If you see my cameras, just like the one you have on the slide, you can have several types of interfaces on it. مثلا هذا. See this servo motor. You hear its sound? It's really strong. See, this servo I have here is like a 180-degree servo. في منهم 90-degree servos. في منهم 360-degree servos, and في sizes, small sizes, في big sizes. The good thing about these servo motors is that they have a feedback mechanism. Inside this box, see, it's big. So if you zoom inside here, جوا في DC motor that moves something, and gears, and a potentiometer that knows how fast or RPMs the motor moved, and it has a stop to stop it. So you can control the actual angle you want to move. If it's 180 degrees for this example, you want to put an arm for it to open a gate or close a gate, you can say go to 90 degrees. Okay. It's really a strong one. Okay. I have a smaller one. مش مشكلة. These kind of motors have a feedback mechanism. They have a board inside. They have a microcontroller inside to tell it how to behave. It has 3 lines. So if you see it on my camera, it has 3 lines. It has power, ground, power, ground, and it gives you a PWM signal here. You give it a command. It's not a sensor, it's an actuator, right? So you give it a command to what angle you want it to go. And now these servo motors, طبعا في منهم 360, يعني they do a full rotation cycle. Okay, I'll talk about them. But these kinds of motors are used to control usually angle or control maybe rotation, and you have feedback. To make these move, يعني you get 3 lines coming out of this. Power, مثلا 9 volt, ground, okay, and a third line, you take it to your microcontroller, okay, and here you write a PWM signal on it. This PWM signal period is usually 99.9999% of the servos. I actually never saw a servo that is different, from different manufacturers. This period is 20 milliseconds. Okay, and the pulse width now relies on the degree. For 100 degree servo that moves from the extreme left to the extreme right a degree, usually the pulse width, it could be plus or minus this amount, but it is usually 1.25 milliseconds for 0 degrees, 1.75 milliseconds for 100 degrees to make this arm turn from here to here, ماشي? And it's linear. You can مثلا in the middle here pointing forward, it's 1.5 milliseconds for this case. So if you wanted to move 45 milliseconds, you can do the math, right? X, if proportional, if at 1.25 milliseconds, 1.5 milliseconds, do this range, and this range different. This is 0 degrees, and this is 90 degrees. So if you want to move 40 degrees, what is the amount of pulse width you want? If you want to go to 45 degrees, what would be the pulse width you want to do? You can compute it, right? You can compute it by 5 minus 1. Is this 5? 1.5. It is 0.25. So the difference is 0.25 here, right? So x minus 1.25. Well, times 4 times, the difference.
بس قسم 2 بتصير 12 ونص ف 1.375.
Yeah, you can do this math, yes. You can do it either this way or here. The 45 degrees are 1.25, and you can figure out each degree, صح? The 0.25 divide them by 90, صح? You know every degree is how much, and add it to this 1.25, and so on. And you can control the speed. Now this range also, for the 360 ones that move 360 continuous, this pulse width, so in this case, the angular position is decided by the pulse width, okay? But for the 360 ones, the pulse width decides the speed of rotation, It has a maximum speed, minimum speed, and you start changing the pulse width to change the speed. طيب. And how do we display this? Well, very simple way. You can say port B 0, make it 1, delay for this amount of time, go back to 0, delay for the rest for 20 milliseconds minus this, صح? And then go high, go low. But this takes a lot of time from your controller. You can do it through an interrupt, timer 0 interrupt. I have an example at the end of this chapter you can use, or you can use the CCP module, which is something we're not going to reach today. Interfacing motors. How do we interface مثلا DC motors? How do I control the speed of this DC motor? We talked about it in principle. We never applied it. And how do we control the reverse yani if this is moving, if I connect to this motor I have here, if I have a battery and a motor, and I connect the positive side to this and the negative side to this part, it will the motor will move مثلا clockwise. To be able to make it move counterclockwise, I need to flip the battery, right? I need to reverse the polarity. So this is, if this is on a robot that wants to move forward or backward, you cannot every time go by hand and flip change the battery polarity. We need to do it electronically, automatic. So this is the last thing I'm going to talk about here: how to control the DC motor speed and how to reverse its direction. How to control speed is something. Sorry.
بس عندي محاضرة في عندي presentation.
Yeah, you can leave. The recording will be there, inshallah.
يعطيك العافية.
Allah يعافيك. We don't have many people left, but I'm gonna keep this recording. So you can connect the motor here as a load. You use a switch, a transistor, a MOSFET, or a regular transistor. You apply a 1 if it's NMOS مثلا, or a negative base. You write a 1. You have a channel. Current will go through the motor. It will turn on. If you write a 0, it will turn off, right? So turning on, off, on, off. If you always write a 1 here, the motor, if this R is a motor, it will move maximum speed. Maximum speed. If you write a 0, it will stop. But if you write a 1 for 5 milliseconds, a low for 5 milliseconds, 1 5 milliseconds, 0 5 millisecond, for example, يعني هذه 10 millisecond, this is also 10 milliseconds, then the motor will be half of the time on, half of the time off. But switching between on and off is really fast. You will not notice it. This will result in average speed of half speed for the motor.
Okay. قصدك 5 milliseconds, صح?
5, sorry. 5 milliseconds. So it will be 5 low. Then the motor is on average moving its half speed. If you go 7.5 milliseconds high, 2.5 milliseconds low, then you're moving مثلا 3/4 of the speed, right? So every time you change this, the amount of being high against the amount you're going to stay low, you will be changing the speed, okay? And we talked about this. Last thing is controlling the direction of a motor. Let me try to build it up easily. So if this is a motor here, if we put a polarity of a volt source, let's say this is a 9-volt battery, then the motor will move this direction, right? To be able to make it to move in the other direction, we need to reverse the polarity, right? Mechanically. Well, another way, if we want to do it automatic, imagine we have a motor like this, and these are its contacts, and this is our voltage source. Imagine we have a switch over here. And we have another switch over here. And we have another switch over here. And another switch over here. And we take this to ground. So this motor, in this case, if we call this switch 1, switch 2, switch 3, switch 4, in this case, when switch 1, let's say switch is open, if its value, and we represent it as 0. If the switch is closed, we represent it as a 1. ماشي, closed.
Yes.
So if all switches were switch 1, switch 2, switch 3, switch 4, were 0, 0, 0, 0, يعني all switches were open, the motor will be, يعني there's no battery, no power source, right? This is open, this is open, this is open. Then there is no power source connected to the motor, so the motor will be off, right? While if we close switch 1 and we close switch 2, what will happen? We will have a path to ground, right? We will have a short circuit. يعني a fire, right? So this is not allowed.
Yes.
Not allowed to close switch 1 and switch 2 at the same time because you'll have a path to ground. Okay, don't do that. So this, you cannot have switch 1 and 2 together, and you cannot have switch 3 and 4 together, right? Switch 1 and 2 is not allowed. Switch 3 and 4 is not allowed, right? So let me put all the cases. 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0. Ah, a lot of cases I should present it in a different way. 0, 1, 1, 0, 0, 1, 1, 1, بعدين 1, 0. Oh my God, this is going to take forever.
16 possible.
16 combinations. Let me do it this way. So if switch 1 and switch 4 are closed, the current is going to flow this path, right?
Yes.
So the motor will move مثلا clockwise. So let's do it this way. Switch 1, switch 2 on. Switch 1 and switch 4, sorry, on. The motor is going to move clockwise. If switch 3 and switch 2 are closed and these are open, the current is going to flow this way, right? Switch 3 and switch 2 are on. It's going to go counterclockwise. If all of them are off, all are disconnected, then the motor is off. If any other combination than these two, يعني it will include 2 of these together, is not allowed, right? Everything else is not allowed. So to control the direction of the motor, we need to control these switches, to have these on together or these on together. How would we do this? Yani, imagine the motor, instead of using manual switches, let's use something like solid state switches or this transistor مثلا, NMOS transistor, something like this. Give it the voltage source here, and take these to make them controller, the motor turn clockwise or counterclockwise. You can have your controller here, 16F877A, for example, right? You can have port B 0 and port B 1. You can connect this one with this one to port 1 مثلا. You can connect this line in black with this line to port B0, right? In this case, the port B0, port B1, let me do it this way. Port B1, if port B if they are both 0, then the motor is what? Then these are all open circuit. The motor is off, right?
Yes, then on.
If port B0 is on, then these switches are closed, right? And port B1 is 0, then these are open. Then you will go, مثلا, motor will move clockwise. If port B1 is 1 and the other one is 0, and the other one, then these are closed. This and this, well, no, this and this. So it will the current will move through the motor this way. So it will move counterclockwise. 1 and 1 is not allowed because it will have these short circuits, right? So 1 and 1, you need to be careful in your program not to turn them together, not allowed. If you see that these are, مثلا, you can just use one pin, and instead of using port B0, instead of, let me write it in what, in red. Another way, and if you can do it this way, you can take, instead of port B1, you can take port B0 here through an inverter, right? خلاص, disconnect this one. So port B0, if it's 0, it will move in one direction. If it's 1, it will move in another direction, right? But how will we turn this off? In this case, you will need a switch here, right? You will need a switch here connected to port B2, مثلا. This will say on, off, مثلا, right? 1 or 0. So to turn on, you write on port B3, a 1 or 0 to turn on and off. And if it's on, port B0 value 0 will be direction, 1 will be another direction. Another way to do it. Okay. Anyways, so to build, they call this an H bridge. H bridge. Why H? Because this shape is like an H, see it? So you can build it using 4 NMOS transistors. But the good news is that you don't have to build it. Today, there are chips. And this is explaining what we did. Well, here he is connecting it in a different way. He's always smart way of protection. He's always maintaining that, making sure that this one is the opposite of this one, so you don't have the short circuit here, and the same here, right? Another way to do it, fine. طيب, look at this circuit. This is actually a dual H bridge chip that you can buy. Let me go open this chip, and I have it here. I think, where is my board? Where's my H bridge guy? Here. If you want to look at it, if you see my camera, it is this chip over here. See this one? I'm going to open the data sheet for this bridge, for this H bridge, this chip. It is on your e-learning. It is on e-learning, but let me just go open it. It is the H bridge data sheet. It's a chip that looks like this. And this is the last thing, guys, by the way, and then it's about coding. They call it a quadruple half H bridge. يعني والله let's go back to our H bridge before the half H bridge. هلا لا خلينا ماشي. You know what? Now, what is this? This is a tri-state buffer, huh? It could be like the NMOS we used in our drawings, the switch. In our drawing, I used an NMOS, مثلا. Here, it's a switch, right? Here, this is a switch. A tri-state buffer could work as a switch, right? You can connect or disconnect. So inside a chip H bridge chip, you find something like this. If you split it, this is one half H bridge, and this is another half H bridge. If I have a motor here, I can connect it to this pin, out 3 and out 4. And I enable this by pulling it to voltage source or connecting it to port B1 and letting go on. Enable. So these are connected. Now, if I take this to port B0, and this is to port B2, and this is 1. So B2, 1, then this is enabled. These are connected. So if you write a 1 here and a 0 here, then the current will flow this way, right? And the motor will turn clockwise. If I write a 0 here and 1 here, then the current will flow this way, and the motor will turn counterclockwise. If I write a 0 here and a 0 here, the motor will stop. Right? A 1 here and 1 here, the motor will stop. A 0 here, and regardless of what is this will be disconnected, then the motor will stop. We can use another motor and connect it to these pins, right? And do the same. Enable 1, 0 to turn in one direction, 0, 1 to turn in another direction, and 0 here to disable and turn off the motor. So you can use half an H bridge to control 2 motors, but you can control them on or off. طبعا, instead of writing a 1 here, you can write a PWM signal, right? Change the pulse width, the PWM, and it will be, in this case, you will be controlling the speed, right? It will be on, off, 5 milliseconds on, 5 milliseconds off, then it will be moving clockwise in half speed. If you write the PWM signal here and a 0 here, it will be move in the other direction, but in half speed. Or you can just write a 1 here, a 0 here, and the PWM on the enable, these 1s and 0s will control the direction, right? And the enable will control the speed, on, off, on, off. So you can have 1 PWM signal instead of 2, one's here and one's here. But in this setup, we use half of the H bridge to control the speed, or controlling on and off a motor, replacing the we did before with using 1 switch. Another way is to use the 2 halves. The 2 halves. So this half, you can use 1 half to control 1 motor, but you cannot control the direction of the motor. You can control the, well, we can control the direction, wallahi. We can. What we did here, right? This is a full H bridge. This is a full H bridge. if I write 1 here and a 0 here, it will move clockwise. If you write the 1 here and a 0 here, it could move counterclockwise. So we control this, the direction of the motor. A PWM here will control the speed. Same here. So these are two H bridges, not two halves. I'm sorry, what I said before is wrong. This is one full H bridge, This is another full H bridge. Okay. So a full H bridge can control the direction and speed. Now, if I erase this part alone, you can get a motor here and connect one side of it to this pin and the other side to ground. In this case, if this is enabled, you write a 1, the motor will turn on. You write a 0, the motor will turn off. That's it. You can have another one here for another motor, another one here for another motor, another one here for another motor. So a full H bridge can use to control 2 motors with speed only, but you cannot control the direction. If you use, so this is half H bridge. This is half H bridge. This is another half. All the two halves is a full. And we have another full here, H bridge, that is also 2 halves. So the 1/2 H bridge would replace this transistor we use to control the motor. So if you have 4 motors, instead of getting 4 switches like this, you can get one chip like this one, dual H bridge, to control each one of these halves will control one motor. Let's look inside this L293D H bridge. They call it dual H bridge because this is one full H bridge and this is another full H bridge, dual H bridge, 2 H bridges. Okay. If we look at the data sheet of this one, this is different serial number, but they call it same concept, quadruple half H bridge, يعني 4 halves, which means 2 fulls, يعني 2 dual H bridge, or 4 halves. Okay, this is what we saw. يعني this drawing here, this drawing here is the same we saw in the slide here. If I erase this, this is the same as this, يعني, but they're هاي محطوطة تحت هاي. Okay, they're put underneath each other. Okay, so this is one full H bridge. This is another full H bridge. We can connect to one Y a motor and the other side to ground. This is half H bridge. If we connect the motor one side to one Y, the other side to 2Y, then we can write a 1 here and a 0 here to make it turn away, or a 1 here and 1 here and 0 here, and make it turn in the opposite way. Okay, and this is for another motor. And this is the pin layout. So this is one. So let me take it here. So if I want to control, if I want to write an example, I'm not gonna do the chip. So let me get this one. If I want to control a motor, I can do this. If I want to control the speed and the direction of a motor, the voltage source, we connect this to this is the voltage source that will power the motor. Okay, so this will be the 9-volt battery, the positive side. And this is the same for the other motor because these are 2 H bridges, 9-volt battery. The ground, these ones, these 2 lines will go to ground, which is the negative side of the 9-volt battery, and this is the 9-volt battery. The positive side will connect here, negative side will connect here, and another one for the other side. It also would connect to the microcontroller ground. So the ground will need to connect to each other. Then, if I have a motor that I want to control its speed and direction, this is the motor. It has 2 wires. So what I'm going to do, if I go to the data sheet again and copy this part, so what I'm going to do, I'm using مثلا the hand side. My motor, this is my motor. I connect to Y3, 3Y, 4Y. So the motor will connect to 3Y and 4Y. Sorry, not 4A, 4Y. 4Y. Now the inputs, 3A, 4A, and enable. A and 4A, I will use them for direction. So port, this will come. Port B0, and this is to port B1. And this enable, I can take it just to high method, take it to 5 volts. So whenever, and we're done. If I have another motor, I can do the same on the other side. But this is done for one motor. If I write a program, I write on port B0, 1 and 0, the motor will turn in one direction. If I write a 1 here and a 0 here, the motor will turn in another direction. If I want to change the speed, I can either, instead of writing a 1, put a PWM signal, or the enable, take it to PWM, okay, and you change the speed. This is a full H bridge, and this is another full H bridge. This is a half H bridge, another half, another half, another half. 4 halves, quadruple. That's why either it's a quadruple half H bridge, as they call it here, quadruple 4 halves, or dual H bridges, and 2 full H bridges. Okay, quadruple half H bridge can be used to control the speed of 4 motors or the speed and direction of 2 motors. طيب. And we're done with theory. We're done with theory, and I just showed how to connect the circuit diagram. This is what we did right now, and these are examples of two codes I wrote previously to control the direction and speed. Let me go to the more, what is this? This code controls the motor speed without direction. Let me go to this one. This one controls speed and direction. Let me start a project and do a class demo, and the other one you do it alone if you want. So project, let me close this one and start a new project and call it control speed and direction of a motor, and call it class demo 15 control speed and direction DC motor. Okay, let me just go copy the code real quick from the slide and copy, Control A, Control V. I'm not done yet. The other half is here. Control A, Control C, Control V, Control What? Okay. Restart. I'm done with the chapter, by the way. It's only this application. You know what? Let me open project. Oh, it's here. It's here. It's opened already. Oh, man. Yeah, it's not it. Build, close, close, close. Project, open project. Class demo 15. Ah, it's not created yet. Project, new project. Here, okay. Next. Let me copy these parts. Let me start a notepad and paste it and take it all together. Because in the slide I had to split it in two halves to show it on a single slide. Copy, paste, then the other half is this one, and paste it here. Then let me take everything and put it here. Okay, this is the code. So I'm trying, what am I trying to do here? I'm trying to control, I have 3 buttons, ماشي, on port C, port C1, port C0, port C1, and this is what I'm trying to do. I want to design a system that I have a microcontroller. I have port C0, port C1, port C2, and I have 3 push buttons here. See? All pulled up to high, all pulled up to high. And what I want to do, I want this is button 1. When I press this button, I want the motor to move. I have a motor here. I have an H bridge. And I have a motor connected to the H bridge, and I showed قبل شوي how to connect it, 3Y, 4Y, right? And let me remember what I wrote. Okay, save. 3Y, 4Y. And I use the enable, and I have a direction on port B. Direction on port B. Port C. Direction. 4. Stop. I'll come back to the code in a second. And these are connected to port B, B1 and B2. Okay, great. So this is what I have. Where's the drawing here? So 1A is connected to port B0. 2A, 3A and 4A is connected to port B1. These are the 3A, port B0, 4A, 3Y, 4Y to the motor. Tamam? The enable, I think the enable, I'm taking it to high. So the enable here, pin, enable pin, enable. I'm connecting it to 5 volts مباشرة. So it's always enabled. And I have port C3 also pulled up to high. So this will control the direction of the motor. This will cause the motor to move in full speed. This will cause the motor to move in half speed. This will cause the motor to stop. This is my example. And I have on port D, okay, port D, I have it connected to a 7-segment display to show the letters F when it's full speed, H when it's half speed, S when it's stop. Okay, this is like a comprehensive example. Okay, so this is the circuit layout. I'm not going to do it physically. I used to do it in class, but the code to do this, first thing I did, I configured the timer 0. Okay, and the initialization here in the main, I configured port C to be input and clear, right? To read the buttons, because all the buttons like port C 0, 1, 2, 3 are connected to ports, the buttons are connected to port C, so port C is input. Port B is going to all be output because I'm going to control it to write 1, 0 or 0, 1 on port 0 and 1 to do the direction. Port D is going to be output because it's connected to the 7-segment display. So if I want to write comments here, control buttons, let's say control buttons connected here, so they're input. Port B, motor speed and direction control lines. So these are outputs. And then port D connected to the 7-segment display to show full, half, or stop. AD-CON1, I route a 06 in it to make port A as a digital port. And I talked about this before. Port A is output. Why do I need port A output? And port A is 0F. So I'm enabling the 7-segment displays because I explained this last time. The common cathode pins for all the 7-segment displays on my port are connected, on my board are connected to port A. So to enable it, I need to write a 1 to that. So here I'm writing F, so I'm enabling all 4 7-segment displays. I defined a variable, unsigned integer, called my button here, my button, and a variable called my direction, unsigned character. Initially, my button is 0 and my direction is 0, initial values. Then in the option register, I set the time of timer 0 to increment every 128 microseconds and with a prescaler of 256 using the oscillator clock 8 megahertz. Same setting as before, okay? Same setting as before. But what did I do this time? Let me show you what I want to do to get the idea. What I did here, I had timer 0. I want, at the end of the day, to control the direction of this motor, I want to do a PWM signal with what? With timer 0. Mashi? Timer 0. I want to do a signal that is 10 milliseconds, period, and 5 milliseconds, pulse width. When this will cause the motor, if I write this to port B0 here, the motor will move in half speed. Okay, this is for half speed. If I want the motor to turn on, so this is on port B0 مثلا. If I want the motor to turn on for full speed, I write a 1 all the time on port B0. طيب. If I want the motor to stop, I write a 0 on port B0. This is in one direction. Now, if I want it to move in the other direction, I write the PWM or the 1 on port B1. ماشي? Here. So I'm trying to generate a PWM signal with 10 millisecond period and 5 millisecond pulse width. How am I going to do that? I know that timer 0, I configured timer 0 to count from 0 to 255 and overflow back to 0 in how much time? It counts, each count, it takes 128 microseconds, right? The overflow happens every 32 point something milliseconds. Now I want it to overflow after 10 milliseconds. So what I did, 10 milliseconds. What I did is that I know that every count is 128 microsecond. So 10 milliseconds is 10 milli. 10 milli is in micro is 10,000 micro, right? And each count takes 128 micro. So I divide it by 128 micro. Okay, and this is 78 counts. So if I have timer 0 count 78 counts, 78 counts is equivalent to 10 milliseconds. So if I start counting here from 255 minus 78 counts, يعني قديش? 255 minus 78 counts 177. بس أنا بدي overflow مش 255 256, I'm sorry, so 178. So if I make the counter start counting at 178, it will overflow after how much? After 10 milliseconds. تمام? When it overflows, it will go back to 0. But the first thing I do in the interrupt service routine, I give the value, I say timer 0 equals 178. So every time I made the timer 0 count from 178 to 255 and overflow. This happens in 10 milliseconds. Got it? So I want to initialize my timer to start counting from 178, not 0, to make it overflow in 10 milliseconds. Now, inside 178 to 255 is 78 counts. So these are 78 counts. What's the half of 78? قسم 78 على 2 30. 78 divided by 2 is 39. So if the timer value is 78, if timer 0 value is less than 178, 178 plus 39, then I am in the first 5 milliseconds. Else I am in the second 5 milliseconds. So I can command, when I'm in the first 5 milliseconds, I can command port B to go high. When I'm in the second, I can command port B to go low. تمام? If I want this to be more than 5 milliseconds, I just play with this number, the 39, right? If I increment the 39, each increment will add to the 5 milliseconds 128 microseconds. So I can make this a variable x, and I can read it from a potentiometer and start changing this 5 milliseconds more or less, right? To change the speed of the motor. So this is the actual code I wrote here. So I started timer 0 counting from 178. I enabled the timer 0 overflow interrupt. Okay. Then in the side, the interrupt service routine, I get here every 10 milliseconds. I know now, right? The first thing I do when I get here is I set the value of timer 0 to 178 because when it overflows, it goes back to 0. So I do put it at 178. Then here, I read the buttons. So I read the buttons every 10 milliseconds. See, even these, I didn't put them in the main loop. I put them here to be more response immediate. I say if port 0, port C ended with 1, I mask everything except C0 is true, then button 1, my button, button C0 is pressed, then my button is 1. Else, if C1 is pressed, my button is 2, and C2 is pressed, my button is 3. And I want to use this for full speed, half speed, stop. And the last button, C4, if it's pressed, every time I press it, I want to flip the direction. If I was going clockwise, I want to say my direction was 1. If I flip it, it will be FF. Sorry, it was 0. It will be FF. If it was FF, I flip it and make it 0, 0. I want to use this to change the direction of the motor. And I clear the flag with the timer 0 overflow. In the main loop, easy. I have 3 cases. If the first button is pressed, I want to move the motor in full speed. But in what direction? If the direction is true, 1, 1, I set port B to 0, 1. Why 0, 1? Because I set, one direction is 0, 1, the other direction is 0, 2. Why? Hey, here. Port B, if port B is 0, 1 or 0, 2. 1 is in binary is 1, 2 is 1, 0. So I'm writing a 1, 0 here or a 0 or a 1, 0 here. So if I write a 1, the motor will move this way. If I write a 2, the motor will move in the other way. Okay? So I'm changing the direction. So if the first button is pressed, I want to move in full speed, but in what direction? If the direction is true, make port B 1, 0, 1 and 1, 0 in one direction, else make it move in the other direction. Okay? And it's always on port B. So it will move in its full speed. And I wrote on port D a 7-1. A 7-1, if you want to, a 7-segment display, if you look at a 7-segment display, can I write? No. But if I want to show the shape of full speed, F, high. You don't see it, but let me show what I mean. To make this look as an F, a 7-segment display that is like this. The blues are going to be off, the red is on. So this is A, B, C, D, E, F, G, and this decimal point is H. So 1, 2, 3, 4, 1, 2, 3, 4, A, B, C, D, E, F, G, H. So to turn on to make the 7-segment show an F, I want to write a 1 here for A, B will be 0, C will be 0, D will be 0, E will be 1, F will be 1, G will be 1, H will be 0. So this is in hex 7, and this is 1. So 0x71 will show an F on the 7-segment display. Mashi, 71. This is where the 71 came from. I want to put it on port D. Then if the other button is pressed, I want to turn the motor in half speed. Mashi. First, I display on port D 76. This is the shape H, and you can do it just like I did the shape F now. Now, if timer 0 is larger than, is less than 178 plus 39, then I'm in the first 5 milliseconds. This is the math we did a little bit while ago. I'm in the first 5 milliseconds. So if the direction is true, يعني one direction, I write to port B1, then or else if the direction is different, I write 2. عشان to make it, to put the 5 milliseconds high on one pin or the other. Else, if I'm in the other 5 milliseconds, either whatever the direction was, port B is going to be 0. I'm going down to low. Okay, so this will result me going high for 5 milliseconds, low for 5 milliseconds, high in 5 milliseconds, low for 5 milliseconds. But which one is high? Depending on the direction, either port B0 or port B1. Last case, if the third button is pressed, I want to stop the motor. So port B is 0 and I display an S on the port D. To run this program, let me build it. Okay, I had the board turned off. Let me try again. And who's left? Ahmed and Abdul Rahman.
موجودين دكتور.
موجودين.
Okay. Let's I'm just setting up my board. Okay. Okay, let me switch the camera. Stop sharing. Switch the camera. I hope you see the camera. What do you see on the 7 segment display?
55 مش كثير واضح الضوء صراحة.
المشكلة هذا is so smart. هذه الكاميرا تاعتي it adjusts the lighting.
Yeah.
It's not 55. It's SS.
okay. SS.
Stop. Okay. رجعت. S. So أنا قلت if I press port C0, I want a motor to lift full speed, right? Full speed. هلا 0 I want just do the pull up. Now I pressed full speed. See, it is F. The motor is turning F in full speed. And if you look at port B, شايفين port B? Again, hi. See here, this here. Port B0 is 0, port B1 is 1. And it's moving in one direction. If I press port C4, 3, sorry, the direction should flip. 1, 2, 3, 4, flip. يعني I'm flipping it continuously. يعني I need to configure these pins of. Okay, to change the direction 1, 2, 3, 4, I can change the direction, but see, now it is moving in the other direction. Now let me change the speed. Now it's full speed, F. If I press the other button, and I'm just directly connecting port C to high or low. If I press the other button, this is H, half speed, شايفينها. And if I push the last button, okay, S, it's back to stop, ماشي, depending on the direction. Honestly, I'm exhausted. I can connect the motor, but I showed the connection, how it's done. I think we're done. So I'm going to end the recording. This is the last thing we're going to cover, this chapter. Thank you very much. And see you if you are interested in the Saturday evening class. It's going to be extra, and I'll cover serial communication. Thank you very much.